All right, so we finished up yesterday with solving triangles, okay, law of cosines. Today we're going to move on and start something new, which is writing complex numbers in what we call trig form, or it's also called polar form. Okay, so I'm going to go through some of the review real quick. Just remember the idea of a complex number. It has a real and imaginary part. Real part comes first. Imaginary part comes second. So in this particular example, A is the real part, B is the imaginary part. Not BI. The I is just there to tell me what's in front of it is imaginary. Okay, another way we can represent a complex number is graphically. And the way you can think of it is almost think of the A and B as a coordinate. Where A is basically going to represent movement on the horizontal axis, and B is going to represent movement on the vertical axis. Okay, we don't call them generally the X and the Y when we're graphing complex numbers. We call one the real axis and one the imaginary. But if you think about it in your head in terms of X and Y, it's basically just like graphing a point. Okay, so A represents movement horizontally, okay, what normally is your X, and B represents movement vertically, which is what is normally your Y. Let's look at a few examples. Everybody have the complex plane? Which axis is which? You could just label it R and I if you wanted. Let's try graphing some of these points. Okay, let's start with -4 minus 2i. Okay, starting from the origin, how would I get to -4 minus 2i? Which directions would I go in? Yeah, Marina?
So you would start on your real axis and you would go 4 units to the left.
Okay, so 4 units left, yep.
And then you would go 2 units down on your imaginary axis.
And then 2 units down. Okay, so that's the point -4 minus 2i. It's like graphing -4 and -2. Okay, Andrew, how would I graph the point -2 plus 3i?
Go to the left 2, and go up 3.
Left 2, up 3. So it's -2 plus 3i. Good. Okay, Silvio, how about 5i?
Two to the right.
I'm sorry, 5i. Third one.
Would you have to split it?
Well, think about what's the real part there.
Oh, you would just go 5 up.
Yeah, the real part is 0. So there is no left and right. This is like graphing the point 5, 0, 5, right? So the real part would be 0, imaginary part 5 up. And the last one would be 6 units right. If you want to think of it as a complex number, write 6 plus 0i. No imaginary component. Any question on graphing a complex number? That's pretty straightforward. All right, so the next thing we're going to look at is how we find the absolute value of a complex number. Well, it's the same idea as if you were doing this with any number. It's always the distance from 0, or in 2 dimensions, we call it the distance from the origin. All right, so let's just look at a picture. So there's a point. If I was graphing this, the original complex number would have been this, a plus bi. So once I graph it, I go right A units, I go up B units, and I put a dot. To find the absolute value, what in this triangle do I need to find the length of? And if I can find that, it'll give me the distance from the origin. What side of that triangle? Oh, Orlando?
What was the question?
What side of the triangle do I need to find the length of there?
The hypotenuse.
Hypotenuse. If you can find the length of the hypotenuse, that will give you the absolute value, the distance from the origin. Okay. How do you find the length of the hypotenuse if you know two of the sides in a right triangle? Oh, Sam?
Pythagorean theorem.
Yeah, we just use the Pythagorean theorem. Okay, so the absolute value of a plus bi, take a, square it, take b, square it, add them up, and then take the square root. Okay, that's the Pythagorean theorem. Let's look at an example. Find the absolute value of 3 plus 4i. Okay, Michael, what's a in this case?
3.
Yep. So 3 plus, and now we just want b. Brandon, what's b in this case? Yep, perfect, just 4. No I, we're just finding a distance. Okay, so just use the 3 and the 4. 3 squared is 9, 4 squared is 16. Okay, add them up, you get 25. So what's the absolute value of 3 plus 4i? Masan? 5. That's it. And that's not an imaginary number, it's a distance from the origin. So it's 5 units. Yes?
I was going to ask if there was a
Nope, because it's a distance. So all distances are real numbers, at least for us. Hey, any question on that? All right, so we've talked about how to add complex numbers by combining like terms. Basically, you combine real parts with real parts and imaginary with imaginary. Well, we're going to look at the same thing geometrically. Okay, we're going to use the same idea. So suppose we have two complex numbers, call them z1 and z2. z1 is a plus bi, and z2 is c plus di. What I've done is I graphed, and again, it's just generic. I don't know what a, b, c, and d are, but I kept them in quadrant 1 to make it simple. So I graphed a plus bi, put that right there, and I graphed c plus di, and I put that right there. Any questions so far? Right. And the idea is that we're still going to combine real parts with real parts and imaginary parts with imaginary. We're just going to do it visually. Right? Which direction does the real axis go in? Is that horizontal or the vertical? Shannon?
horizontal.
That's the horizontal. Okay, so let's draw just the horizontal component of AB. There's your horizontal component. Okay, it's going to be kind of hard for you to do on paper because I'm going to take all these and I'm going to kind of stack them together. Okay, but I'll just keep it there for now. Now I'm going to draw the horizontal component for CD. I'm going to move it in a minute. Now I'm going to draw the vertical components. Okay, the vertical components are the imaginary. Okay, so AB has that as an imaginary component, and CD has that. All right, so the idea is if you take all four of these, not that, that, and that. If you take all four of those and put them together, you can basically figure out if we added these where they would be. So you just start at the origin, and you just stack them all together, connecting the end of one right to the beginning of the other. So if you were to combine those two together, that's what you would get. Okay, that's the idea. Now, it doesn't matter how you do it. You could combine, let's see, you could go take this one, put that, and you could put that, and you could put that. Because we're adding things together. You can think of it as like the commutative property. Changing the order still gets us to the same spot. Right? So the idea is you're combining the real parts together and the imaginary parts. And A plus C visually would be represented by this. That line in green, that is your new horizontal component. And the line in black, visually, that's my new vertical component, or real and imaginary. So it just gives you a way to visualize what this would look like on a grid. Any question on that idea? Most of the time we're not going to do it visually because it takes a long time to draw. We'll just add it up like we have in the past. I just wanted to show you that idea. So we'll try this one. We've got 3 plus 5i minus 2 plus I. Okay, what should I get? Let's just write down what we should get, and then we'll do it visually. This isn't written in the standard form of a complex number, but when you give me your answer, try to write it in standard form. Actually, no, that is standard form. But yeah, make sure when you write your final answer, it still is in standard form. Yep.
It would end up being 1 plus 4i.
So we got 3 minus 2. Yep, that's 1. And 5i minus I, 4i. Okay, so that's what we should get. Let's try it visually and see what happens. So we're going to go right, let's make it a little bigger. Right 3, up 5. Right 3, up 5. And then we're going to go right 2. Or you know what? Might be easier to distribute that negative first. Think of it like this. 3 plus 5i, that's fine. But think of it as this one. Plus negative 2 minus I. Right, so here's your two numbers you're adding. Any question on the distributive property there? Okay. So I'm going to go left 2, down 1. Left 2, down 1. Okay, let's draw our components, and we'll stack them together. I'll put an arrow so we know which way things are going. So we went right 3, left 2. Right, so we've got our horizontals, and let's do the verticals. We have an up 5, and then we have a down 1. I'm going to take all those arrows and stack them together from the origin, and that'll tell us where we end up. The other reason I'm doing it this way is because this kind of starts to introduce you to vectors, which we're going to talk about in section 8.5. Stacking things together, just like this. Take the end of one, connect it to the beginning of the other. Okay, so all the arrows are pointing in the same path. Take this last one, and we end up right there. Okay. Right 1, up 4. Yep, that's exactly what we should have done. Okay, any question on that? Right, so just a visual way to add complex numbers. Not very fast, not very efficient, but it's a different way to think about it other than just doing arithmetic. Okay. Right, so now we're going to look at how we write a complex number in trig form. Okay, so we're going to start out by putting your point. And because we're dealing with an x and our axes now, I'm going to use x and y rather than a and b. Because we're going to start talking about graphing things more, so it might be more comfortable if we use x and y for the letters. Okay, so on my real axis, I moved x units to the right. On my imaginary axis, I went y units up. That gives me two sides of the triangle. This is the third side I'm going to call r. And then I'm going to put theta. Okay, there's an angle in here between the real axis and the hypotenuse that's r. There's some angle there. Okay, and the reason we're going to think of this hypotenuse as r, because eventually we're going to think of that point as being on part of a circle. Right? So it's really like a radius. It's a distance from the center. For now, you don't have to think about the circle, but that's why I'm using r. Okay, I want to find two things. I want to find x and y, but I want to write them in terms of r and theta. Right? So I can use two trig functions to do that. Okay. Start with cosine theta. Tahina, if I found the cosine of theta, it would equal what over what?
Y over
So what's cosine? It's what? That's sine. Yep. Adjacent over hypotenuse.
X over Y.
Good. So it's x over r. I'm going to rewrite it and solve for x by multiplying both sides by r. So I get r cosine theta equals x. I'm going to do the same thing down here. Sine of theta is y over r. I'm going to rewrite it by multiplying both sides by r. And I get r sine theta equals y. Now I'm going to make a substitution. When we wrote our complex number as x plus iy, this is rectangular form. It's rectangular form because x is left and right movement on a grid. Okay, y is up and down. Oh, we have a new way to write x now. We now have a way to write x in terms of a distance from the origin and an angle. So we're going to use that instead. And same thing there. Okay, we have a new way to write y in terms of a radius, distance from the origin, and an angle. Okay, so if you make that substitution, instead of x plus iy, you get r cosine theta plus the I stays right where it is, times y, which is r sine theta. Now, since there's an r that's common to both, they usually factor that out and write it like that. R cosine theta, or r parentheses, cosine theta plus I sine theta. This is the trig form of a complex number. All you have to do is find out what r is and what theta is. So r is your distance from the origin, and theta is the angle from the positive x-axis. And our point can be in any quadrant. So you could have angles that are acute, like the pictures I've been drawing, or maybe they go into quadrants 3 and 4, and you start to get obtuse angles. Okay, so if you're in quadrant 3, your angle would have to be more than 180. Quadrant 4 would also be more than 180. We can write angles as positive or negative. Generally, we'll stick with positive angles. And remember, if you ever came up with something like cosine of negative x, say your angle was negative, on the cosine part, if you have a negative angle for theta, you can just get rid of the negative. Try it. Try 15 degrees, take the cosine. Now do negative 15. It's the same thing. So when you have a negative on your angle with cosine, it can just go away. With sine, the negative doesn't go away, but does anybody remember where we can put it? We can take it away from the angle and put it somewhere else. Justin, do you remember where we can put that negative? We can take it away from here, but it's got to go somewhere else. Where else could it go, really? You want to see where it could go? This is your whole expression, so there's only one place we could really put it.
You can make it a negative sign of x?
Yeah, you can just put it in front. Right, so that's one way of dealing with negative angles. Cosine, it goes away. With sine, you can take the negative and put it in front. Right, so what would that do? Instead of being a plus I sine theta, if you had a negative, it could be minus I sine theta. Okay, so minus I sine theta is okay. If sine is a negative, or if theta is a negative angle, that could happen. Okay, another way to deal with a negative angle is to add 360 to it. The only problem with that is then your angle gets really, really big. So if you had like negative 10 and you add 360, then it becomes 350. This, I would say, is a more eloquent way of dealing with a negative angle than just adding 360. All right, so how do we find r and theta? So here's your triangle. That's x and y. How do you think you'd get r based on knowing x and y? Taylor?
Do you have any angles? Like, would you do the...
We're going to have to find an angle, actually, that angle. But we don't have any of the angles right now, but think about what kind of triangle that is. We don't need law of sines or cosines because it's a right triangle. And help her out. How do you find the third side when you know 2? You're going to know x and y. Yeah.
Pythagorean theorem?
Yeah, the Pythagorean theorem. So if you know x and y, just use your Pythagorean theorem, and that'll give you r. Okay, and then to find theta. Which trig function could you use to find theta if you know x and y? Would you use sine, cosine, or tangent? Yeah. Yeah, you'd use tangent. Tangent is opposite over adjacent. And that wouldn't give you theta directly, but it would give you tangent of theta. And so, Silvio, how would you get theta by itself?
You take the inverse tangent.
Yeah. Inverse tangent of y over x. Now, inverse tangent is always going to give you an answer between negative 90 and 90. So that's going to work fine for quadrants 1 and 4. 2 and 3, we're going to have to make an adjustment because you'd never get an answer that's in quadrants 2 or 3 with that formula. All right, so to find r, just use your Pythagorean theorem. If you're in quadrants 1 or 4, use the formula we just figured out. Inverse tangent of y over x. If you're in quadrants 2 or 3, okay, basically instead of trying to find an angle on this half, we're going to shift it to the other half. Well, how would you shift this halfway around a circle? You'd add 180 to the answer. And that would give you an answer in quadrants 2 or 3. So add pi if you're doing it in radians. Add 180 if you're doing it in degrees. Now, this still doesn't cover all the possibilities. Besides being in quadrants 1, 2, 3, or 4, where else could your angle be? Yeah?
It could be on one of the axes.
It could be on an axis. And it's particularly hard to deal with using this formula. Let's say x was 0. So you had the point 0, 3, up 3. Well, you can't use this formula to find it because you'd be dividing by 0. So if a point is on an axis, you only have 4 choices. It's either 0, 90, 180, or 270? Or 0, pi over 2, pi, 3 pi over 2. Okay, so for one of the quadrantal angles, you just have to know by looking at it, if it's up, that's 90. If it's left, 180. If it's down, straight down, 270. For anything else, you can use these formulas to find your angle. Okay, so let's find the trig form for this number. Negative 2 plus 2i. So remember, the goal when we're done here is to find out what's r, what's theta, and fill them into the formula r cosine theta plus I sine theta. If it helps, I would make a sketch, at least to figure out which quadrant you're in. I'm sure some people can look at that and figure it out, but it's left 2, up 2. Right, so that's a quick sketch, that's where we are. And first thing I'll do is find r. Okay, so in this case, r squared is going to be 2 squared plus 2 squared. So 2 squared is 4, plus another 4 is 8. We get the square root of 8, which, what does the square root of 8 simplify to? Yeah.
2 square root 2.
2 square roots of 2. Good. Okay. That's our radius. Just put it off to the side. We're going to need it when we write our final answer. Now we need theta. Well, there's two different formulas. Do we use inverse tangent y over x or pi plus inverse tangent? Which one am I going to use this time? What's that?
Pi plus tangent.
Right. I'm in quadrant 2. I got to use pi plus inverse tangent. And remember y, that's your vertical. X is your horizontal. So in this case, my vertical, I went 2 up. But my x was negative because I went left. And there's a negative in the problem. Okay, so we're finding the inverse tangent of negative 1. All right, so okay, we're doing this in radians. So plug in negative 1, inverse tangent. That's negative 0.79. Then don't forget we've got to add pi to it because we're in quadrant 2. It's about 2.36. Okay, if we want to round it off, which is fine. If you wanted it exact, the way I would do it is do this in degrees and you'll get a nice answer. Okay. If you did inverse tangent of negative 1 in degrees, you're going to get negative 45. And then if I add 180 to it, I can see very easily the angle is 135. Okay. Or if you did it in radians, that's 3 pi over 4. I would never recognize 2.36 as 3 pi over 4. I just don't know that decimal. But if I check it, 3 times pi divided by 4, it's exactly what I have. So if they want an exact answer, my recommendation, do it in degrees. You'll get a nice answer usually. Then change it to radians. Okay. But I want you to just see the process of how you're. Okay. Now we just put our final answer. So the final answer is r cosine theta. So let's look up. R was 2 square root 2. Our angle is 2.36 plus I sine theta. And that's the final answer. You don't do that out. If you distributed the 2 root 2 to each part, took the cosine of 2.36, took the sine of 2.36, change this answer exactly back to what we started with. Okay. So we're not going to change it back. You leave your final answer just like that. And again, this was, if we did it exact, it was 3 pi over 4. They'll specify in the directions if they want it rounded or exact. Okay. Any questions on that? So that's how you write a complex number in trig form. Use the Pythagorean theorem to find the radius. And then use one of these two formulas to find the angle, unless it's on an axis. Then your choices are pretty limited. All right, so what trig form really does, what it makes very, very simple, is multiplying and dividing complex numbers. Okay, let's look at the old way we had to do this. Anyone remember when we did division of complex numbers, what did you have to multiply top and bottom by here? This was a trick, so it's going to cancel out all the imaginaries in the bottom. Marina?
You multiply it, so you would, in order to get rid of it, it's kind of like rationalizing. You would multiply it by 5 minus I.
Yep. So you multiply by, does anybody remember what that's called? Yes.
Conjugate.
Good, the conjugate. So that's the conjugate. All right, so that's the first thing you got to remember. You got to remember, okay, I multiply top and bottom by the conjugate. Now I got to do the distributive property in the top. I get 15 minus 3i. Now in the bottom, there's a trick, or if you don't remember the trick, just FOIL it out. I got to do 5 times 5. 5 times negative I, 5 times positive I. Those cancel. And then I get I times negative I, which now I need to remember what that is. It's positive 1, because that's negative I squared. And remember, I squared is negative 1. So it's negative negative 1, which becomes a plus 1. Right? And we're still not done. So now we write the top. And to put it in standard form, you need to take the real part and the imaginary part, put them each over 26. So that's your answer. 15/26 minus 3/26i. Okay, that's how we had to do division of complex numbers before. Okay, there's at least like 5, 6 things that could go wrong here, whether it's foiling, combining like terms. I didn't even give you one where you had to do a double distributive in the top, but that can also happen. There's too much that could go wrong. So, I'm going to take a look at how we can multiply and divide complex numbers in polar. Okay, multiplying and dividing complex numbers in polar, or I say polar, trig form, same idea. Just a different word for it. Very easy. Figuring out what makes it so easy, not so easy. So we're gonna look at, it's actually a three-step proof, the way the book does it, of how you can multiply these and divide them in trig form. First thing, obviously, is your numbers have to be in trig form. So if they're not written with R and theta, that might be too much extra work. It may not make this process worth it. But if they're already in trig form, this makes it very simple. All right, so let's just write those out, okay, multiplying them. I'm going to do z1 times z2. So we've got z1 times z2. I'm not going to go through the proof for the division, but you kind of need a lot of room horizontally to write what we have to write out. So we've got r1 cosine theta 1 plus I sine theta 2. And make sure you put parentheses around that because that r1 is distributed. And we're going to multiply all of that by z2. r2, again, put a parenthesis because it's distributed. Cosine theta 2 is I sine theta 2. Now, this isn't really hard. It just ends up taking up a little bit of space to get the formula. Eventually, there's going to be two trig identities that cause this whole thing to become very simple. Yeah?
In the first one, why is it sine theta?
Thank you. You gotta be very careful. Keep the theta 1s and theta 2s straight. We cannot mix those up. Theta 1 just represents some angle in the first complex number. Theta 2 is a different angle. It could be the same, but it doesn't have to be. Right, now we're going to distribute this out. Unfortunately, I think I might have to write it on 2 lines, but we'll do the best we can. And let's see. You know what, before I even distribute it, if you just want to watch this step, I'm going to take R1 and R2, and I'm going to put them in front. Basically, it's like I'm going to pull that out in front. So we don't have to, basically, we don't have to worry about that for this whole problem. So just take R1 and R2. And I'm going to write everything else I just had now, except the R1 and R2 are now in front. All right, so we get cosine theta 1, I sine theta 1, and let's do cosine theta 2, I sine theta 2. And that's perfectly fine to rewrite it that way. All I did was use the commutative property of multiplication. I'm multiplying 1, 2, 3, 4 things together. I just reordered 2 of them. It's like 3 times 7 and 7 times 3. Same thing. Now the part we're going to FOIL. Okay, so we're going to FOIL out that entire second part. All right, so we get R1, R2. We're going to get cosine theta 1, cosine theta 2. Okay, next part. I'm going to put the i's first. I cosine theta 1, sine theta 2. Do the inner, and I get i's again. I'm going to do I sine theta 1. Cosine theta 2. This is much easier when you use actual numbers. You don't have to worry about this. Okay, and then the last part. I have I times I, which is an I squared. Okay, that becomes a -1. Sine theta 1, sine theta 2. All right, so we have all that when we distribute. Now what I'm going to do is regroup it so that all the imaginary terms are next to each other and the 2 real terms are next to each other. And then I think you'll start to see a pattern. All right? So basically, let's just take this last term and put it up right after the first one. Yeah?
Is that the part that's below the rest of it? Is that supposed to be a subtraction symbol?
Yep, that's a subtraction symbol. Yep. All right, so let's write what we had before, cosine, cosine, but then put minus sine, sine. It's kind of my first hint. That's how I said it when we learned what I'm thinking of, that I'm hoping you're thinking of. So we have cosine, cosine, minus sine, sine. Before I keep going, anybody kind of recognize that a little bit? You don't have to know exactly what it is, but cosine, cosine, minus sine, sine. A little bit. This was on your last test. Okay. And let's do the next part. Since they both have i's, let's factor that out. I'll just put it down here. So I'm going to have I cosine sine, cosine theta 1, sine theta 2, plus, this part also has an I, but I factored it out. Sine theta 1, cosine theta 2. All right, let me highlight two things that are going to simplify. This is something special. Cosine, cosine minus sine, sine. And this is also something special. Cosine, cosine, sine, sine, cosine. Anybody recognize that first one? Cosine, cosine minus sine, sine. And if you need a hint, it was an identity from section, let's see, 7.5. Nick?
It's cosine of theta 1 plus theta 2.
Exactly. All of this is just cosine theta 1 plus theta 2. This is the formula for taking a cosine and splitting it as a sum. So all we had to do is add the angles. Right? So we'll just replace everything that's highlighted in yellow with this. And how about the second one? Cosine sine plus sine cosine. Anybody recognize that one? Yeah.
It's sum of sine.
Yeah. This is the formula for the sine of a sum. So when we split things, it's like 30 plus 45. So this, all this bottom stuff in yellow simplifies to sine theta 1 plus theta 2. Right, so let's write the final answer nice and neat. So it's R1, R2, and then the first thing I highlighted in yellow becomes cosine of the sum of the angles. Second thing is plus I. And that whole bottom thing I highlighted in yellow is the sine of a sum. If you didn't recognize that, it makes this formula very hard to come up with. So all you have to do, if you want to multiply two things together in polar, take the two radii, multiply them together. Take the two angles, add them up, and you're done. You don't need to use conjugates. You don't need to FOIL. You don't need to remember I squared is -1. None of that. Okay? Just take the two radii and multiply them. Take the two angles and add them. For division, I'm not going to go through the proof. It's similar. But there's only two things that are different if you want to divide complex numbers using trig form. Take your radii and divide them. Take your angles and subtract them. That's it. No foiling, no I squareds, no writing things with separate denominators, none of that. The only thing R2 can't be is 0, obviously, because you can't divide by 0. And again, this assumes that the numbers you want to work with are already in trig form. If they're not, maybe it's too much work to change them into trig form and do this than to just do it using conjugates. Right? But you don't have to go through this proof again. You just need to know those two formulas. Everyone have the two formulas? All right, let's look at an example. Okay, to save a little time, because I knew we'd be getting close, what I did is I wrote down two complex numbers in rectangular form. I converted them to trig form. Okay, how do you do that? Use the Pythagorean theorem to find R, and then use inverse tangent to find your angle. Okay, we did that in an example previously. And now we're going to find z1 times z2. Okay, to find z1 times z2, what do I do with my two radii? Michael? Yeah, we're going to multiply z1 times z2. What do we do with those radii?
You multiply?
Yeah, you multiply them. So we have 5 times 2 times the square root of 2. That's 10 square root of 2. We're halfway done. That's my radius. 5 times 2 square roots of 2 is 10 square roots of 2. And now I need cosine of my angle plus I sine of my angle. How do you get your angle when you're multiplying? What do you do with the two that you had? Marina?
You add them.
You add them. 0.93 plus 2.36. So it's 3.29. And that's the same angle for both. And that's it. That's the whole answer when you multiply two complex numbers using trig form. Just multiply your radii, add your angles. Okay. What about when I divide? What do I do with my radii when I divide? I'm going to take 5, we're going to take 2 square root 2, and do what with them, man?
5.
Yeah, we're just going to divide them. For now, I guess the only thing you could really do with that is you could rationalize the denominator. So you could make it 5 square roots of 2 over 4. Why don't we write it like that? So I just divided my two radii and got the square root out from the bottom.
Would it be 10 square roots of 2?
5 over 2 square root 2. 5 square roots of 2 over,
Oh, you leave the 2 in there.
yeah, over 4. All right, and now I need my angle. Make sure you put parentheses so that radius is distributed. Nick, what do I do with my two angles I had to get my new one?
Yeah,
So we add them when we're multiplying.
yeah, subtract them.
Subtract them. We're going to get 0.93 minus 2.36. Okay, that's negative 1.43. Okay, what I'm going to do is this. I did two things. First of all, I had a negative angle on a cosine. We said that a negative on a cosine can just go away. The negative on the sine can't go away, but it can go in front. So I simplified that at the same time. And that's your final answer. Okay, so just remember those two steps. Either multiply your radii and add your angles, or divide your radii and subtract your angles. And it makes complex arithmetic with multiplication and division a lot easier. All right, so the homework, it's on 450. Okay, I'd like you to try 1 through 3, 5, 8, 10, 11 to 15, 17 to 21, 33, 34, 37, and 47.